Hi. Thanks for joining the IS Academy this afternoon. And those of you who are joining from Europe this morning, good morning and good afternoon to everyone. Let me start by saying thank you for taking the time out to actually come and join this session. Before we get started, I just want to make sure whether I'm audible. So if I could just have any kind of thumbs up in the chat, if you're able to hear me, then that would be awesome. Am I audible? Great, thank you. Okay, so let's get started. So today's session is an introduction to Amazon VPC. If you're interested in working in the AWS platform in cloud computing, if you've already started working on AWS, maybe you've even got some certifications, then hopefully this session today will be really beneficial to you. It is an introductory beginner course to the networking section of the AWS platform. And it's a section that's taken off from the AWS Certified Solutions Architect training program that we provide at the IIS Academy. So we'll get started. Probably the best way to start is I'll do a quick introduction of who I am, and then we'll jump right into it with an agenda. There's some theory to cover. Some of you might be relatively new to AWS and indeed to the world of networking. So there is a precursor to actually getting on and talking about virtual private cloud in AWS. And that is just to give you a brief high-level overview of what networking is all about. It's by no means a deep dive, but it's to benefit those of you who are really new to the AWS platform, to networking and cloud computing in general. And then we'll swiftly move on and start talking about how VPCs are built. And I'll be doing a hands-on demonstration on building out a VPC in the AWS environment. If you stay right till the end, there is also a special offer if you're interested in taking on further training, especially with the solutions architect. So I hope you do stay right at the end, and I hope you find this course really useful. So as I said, the course is just a quick overview of covering a lot of building your first VPC in the cloud. And in terms of who I am, my name is Rajesh, and I'm a senior solutions architect with over 20 years of experience. I actually come from a Microsoft background originally, and then moved on into AWS about 10 years ago. But over the last 20 years, I've been working very closely with AWS and Microsoft, mostly around the 365 platform of Microsoft. And my journey has been predominantly to help clients migrate their on-premise workloads, their on-premise solutions to the cloud. I've worked with large range of companies, startups right up to companies like the Big Four, and I've helped a number of companies move to the cloud and embark on their digital transformation journeys. About 7 years ago, I got into corporate training, and I've been doing corporate training ever since. I've worked with a number of L&D companies, learning and development organizations. I've been part of the AWS Restart program, as well as building a lot of bespoke training solutions for various clients, again, on a global level. I deliver live instructor-led training as well as self-paced training services on AWS at this point in time. And I also offer career guidance for anyone who's looking to either get into the cloud, or perhaps you have been working in the cloud environment and you just want a bit of an understanding of what trajectory to take based on your interests, passion, and what you enjoy about your career. So we can talk a little bit about that as well later on. And I'm also a successful author. I've been able to publish 3 separate books with Pact Publishing. 2 of them are with Pact Publishing. One is self-published around the solutions, around the Cloud Practitioner and the Developer Associate programs. So that's enough about me. Let's talk about the agenda for today's program. So a high-level introduction on on-premise networks, only for those of you who are starting off new into the world of cloud, into the world of networking. A high-level overview of IP addressing and port numbers, which are really the prerequisites of building any kind of network, whether it's on-prem or in the cloud. Building networks in the cloud. So this is where we introduce you to Amazon VPC, which stands for Virtual Private Cloud. Amazon VPC architecture. We'll take a look at the architecture that we'll build in my AWS account, but also what a typical real-world architecture might look like. So you have a bit of a reference point to work from. Amazon core components, so VPC core components, which are all part of the lab build out. And then We'll then dive into any Q&A that you might have, any questions that you might have about networking in the cloud, followed by, as I said earlier, if you stay right to the end of the program, I've got a special training offer for you if you're interested. Okay, so let's get started. So before we do, just a quick housekeeping. I'm trying to make sure that this session stays within the time frame allocated. So what I want to do is I want to run through a lot of the theory as well. And then what I will be doing is as we jump into VPCs, I will be demonstrating this in my AWS account. Feel free to obviously have any questions that you might have. However, I am going to leave questions to the end for the Q&A session, just so that we can cover everything that we need to cover. And then obviously the floor is open for you to ask your questions. Okay, so let's get started. So quick introduction to on-premise networking for those of you who are new to the world of networking. So what you're looking at on the screen is a typical, very simplified on-premise network. Okay, this could be even a home office. It could be a small startup, or it could be part of a big data center operation for a large corporate client. You'll see on the screen that I've got desktops, laptops, Wi-Fi routers, servers, and so on. And essentially, a network basically consists of two or more devices connected to each other, either over a wired or a wireless link to enable the sharing of resources, such as data, applications, hardwares, such as printers and photocopiers. So we, in a corporate office, will share printers. We wouldn't have a printer on each desk. That was, many, many years ago. We went away from that thanks to the world of networking. And these devices are all connected to each other over a network served by a common or more than one or more router interfaces or network interfaces, such as this Wi-Fi router over here. So in your home network, obviously you're going to have, some desktops, some laptops, maybe you've got a tablet, maybe you've got a shared printer, but what's serving all of that to allow that network connectivity is your Wi-Fi router. So it's an isolated environment to share resources between nodes. So these things are called nodes. And the communication speed, performance, and reliability is going to be based on the type of cabling you use, if you use a wired network, or if it's a Wi-Fi system, what kind of Wi-Fi system you're using, what speeds you're getting, that kind of thing. And obviously the capability of the network device itself, in this case, the Wi-Fi router. You can define and limit both inbound and outbound access into and out of your network using physical connectivity, obviously. So if we take this device and we disconnect it from the actual network, then it will be completely isolated, as well as using things like firewalls, whether that's software or hardware firewall solutions. So how do these devices communicate with each other? And most of you hopefully already know this. For those of you who don't, it's via IP addressing. Okay, so all of these devices need a unique IP address. And essentially what that means is each and every device on that network has got within it a network interface card. This could be a wired card or a Wi-Fi card. If you've got a laptop and you're looking at this on a laptop or on a phone, you've got a wireless card, most probably. But it's the card that gets the IP address, and it can have one or more IP addresses. So let's talk about IP addresses. IP address stands for Internet Protocol Address. Each device on a network is assigned a unique IP address before it can participate on the network. This is important. It's like, you've got to make sure that everyone has a unique phone number in order to be able to dial each other. You can't have two devices, two phones with the same phone number with the same SIM. Okay, that doesn't work. In the same way, every device on a network will have a unique IP address in order for it to communicate on that network. An IP address is a unique string of characters or numbers that identifies the computer it is associated with on the network. And as I said earlier, no two devices will have the same IP. So something like 192.168.1.5 is a typical IP address in a home network, also used in a lot of corporate networks as well. But this is what we call an IPv4 address or version 4 addressing scheme. This is widely used and it's been used for a very long time. And we still use it till this day, even though it has a lot of limitations. So how do we get these IP addresses? Well, you can actually just get onto your computer, go into the command prompt, or if you're using Linux, the terminal, or Mac, the terminal, and actually assign it an IP address. Or you can use something called a dynamic host configuration protocol server. This is an application that has the job of assigning IP addresses to devices on the network that it's a part of. So in large organizations, we will have separate servers that do that job. But in your home network, your Wi-Fi router is doing that job. So your Wi-Fi router is acting as a DHCP server as well. And it is assigning all your devices, your laptop, your phone, your mobile, your desktop, your printer, with an IP address. Once you connect it to the network, either via Wi-Fi or via a wired connection, they will seek out a DHCP server, unless you've already assigned it an IP address. And it will request the DHCP server for an IP address so that it can participate on the network. In terms of how it actually works, well, it's quite simple. It will dynamically assign an IP address to a device or a node on the network to enable communication using IP. And devices and nodes will accept an IP address from the DHCP server. Those devices are called DHCP clients. So a client-server relationship there again. DHCP servers are configured with a pool of IP addresses. Sometimes you might have found that, when you have a lot of guests come at home, some of them are not able to get onto your Wi-Fi network. And if you are a techie and get onto your route and see what's going on, you might even see an error saying that you've run out of IP addresses. That's because there's a limit in your pool. And based on the limit of the pool, so many devices can join the network because so many devices will need an IP address, a unique IP address each. So as well as IP address information, the DHCP server will assign other TCP/IP configuration information, like what are the DNS servers, are there any gateway servers to connect to, that kind of thing. So how does it work? Well, your device, when it joins the network, whether via authentication on the Wi-Fi router or via a wired connection, it will send out a broadcast message to discover if there are any DHCP servers in that environment. The DHCP server, if it exists, will make an offer. It will send an offer packet to the client with an IP address and any additional configuration. The DHCP request process is when the client then sends a request broadcast requesting that offered IP address. It's saying, oh, thank you for the offer. Yes, I'd like to have this IP address. And then the final step, step 4, is an ACK step, an acknowledgement step, where the DHCP server resends that IP information, confirming that this client now has that IP. What it does is it assigns the IP to that client's MAC address, the client's network card's MAC address. And there is the connection between the client and the actual IP address. And the DHCP server will maintain a table of all assigned IP addresses. So it knows which machine is connected to what IP address. So that's how it works. You can learn more about it if you're interested in how DHCP servers are configured, how they should be deployed, what are best practices, by clicking on that link over there if you're interested. Okay, let's talk about larger networks or wide area networks. We spoke briefly about local area networks, the home network that you have, but obviously you work for organizations that may have multiple branch offices. And here you can actually connect your different offices over private network connections. You can do so over the internet using what you might have already heard of VPN technology, but you can also build private connections between those locations. So this is a UK-based company. They've got their corporate office in London, one in Manchester, one in Glasgow. We can connect over a wide area network using a telecommunications provider, MPLS network, that kind of thing. What I do want to draw your attention to, and we'll revisit this again, is that you will note that this company, which has 3 offices, have got different ranges of internal IP addresses. This is important, and I'll come on to why in a bit. Also, you can connect your network to the public internet. So whether it's your home office, a startup, or a corporate data center, we connect to the network. We connect to the public network, which is the public internet, using some form of gateway. So we've got a router device, but this device is also acting as a gateway. So what is a gateway? A gateway is basically something that allows you to connect networks by performing what's called translation between different protocols and data formats at the network boundary. Gateways serve as an entry and exit point so that all data passes through it before being routed to its final destination. In simple terms, a gateway is literally that, a doorway, if you will, to another network. And if you take a very close look at this device, you will notice that it's got two IP addresses. This is an internal IP address that seems to have a similar range as the internal network, and that's an external IP address, or what we like to call a public IP address. If any of these devices need to talk to each other, they can just send IP packets to each other. But if they need to send a request to Google or Amazon or whatever, that's not in the internal network. They forward that traffic to the router, to the gateway, and the gateway forwards it onto the public internet. So that's how gateways and routers work. They allow you to send traffic to external different networks based on how you build out your route table. We'll talk about route tables a little bit later. But essentially, what I want to draw your attention to is the fact that all of these devices are able to access the internet via that gateway. And that's the same way how your home network works as well. So you've got a Wi-Fi router which is connected to your ISP, okay, whether that's Airtel or whether that's, Verizon or whatever it might be, depending on where you are. Your router is acting as a DHCP server, as a network connector router, but also as a gateway. So let's talk a little bit about IP addresses next. So we've got two different versions of IP addresses, version 4 and version 6. So version 4 has been there for years. Version 6 has also been there for a few years now. But version 4, or IPv4, is a 32-bit address scheme. Well, what that means is when you convert this decimal number to binary, you have 32 binary bits of ones and zeros. And IPv6 has a 128-bit addressing scheme, and it's massive. Why is that important? We'll come to that in a second. Let's take a look at an IPv4 address. The format is very simple. N.N.N.N. Each of these N's is what we like to call an octet. It's called an octet because there are 8 bits in each of these numbers when you convert them to binary. And so in decimal, each bit can range between 0 to 255. That's in decimal. But in binary, if you convert 0 to binary, that's 8 zeros, and 255 is 8 ones in the binary format. So it can range anything from 8 zeros to 8 ones. And that's for each of the octets you're looking at. So when you convert all your IP addresses, the 4 octets, into this binary, that's 32 bits of ones and zeros. Each device that you have on the network will have an IP address in decimal, but when it talks in machine language and machine communication, it's obviously going to convert that to binary as well. And in binary, it's 32 bits in total. So that gets converted to its 32-bit equivalent binary format. Also, understand that because we've only got 32 bits in this range, and because we're doing in binary, 2 to the power of 32 gives us something like 4 billion odd IP addresses. So that means on the entire planet, if we're using IPv4, we've got 4 billion IP addresses to work with. And hopefully you realize that that's just not sufficient in 2025. So IPv6 came about, again, quite a few years ago, but it comes with 128-bit addresses. And actually, when you look at how it works, it's divided into 8 groups of 4 hexadecimal digits. And when you convert it, it gives you 2 to the power of 128, which is, whatever that is, right? That's a huge number. And hopefully we'll never have enough devices to occupy all of that range. Now, the problem with 32-bit addresses is that we've only got 4 billion odd addresses. But this thing is, IPv4 is widely used, and it also supports a lot of legacy systems. So even today, even in 2025, although a lot of networks are using IPv6, you will find that when you work in cloud computing, you will need to incorporate IPv4. And IPv4 will generally be your default unless you're building a greenfield project that from the very beginning is going to be purely IPv6. And then depending on who's connecting into that application or solution that you're building in the cloud, they will all need to be operating on IPv6. In most cases, we're definitely heading in that direction. But even today, we're still using IPv4 as a default. So the question then arises, if there are only 4 billion odd IP addresses, how is it that we manage to still communicate? How do all these devices work on the network? And the fact is that not every device needs to have a unique IP address on the public internet. Okay, so I mentioned right at the beginning that every device that needs to communicate in a network needs a unique IP address, but not every device needs to be accessible from the public internet. So when you have your home network or your startup or your large corporate organization, these devices, they may need to access the internet to download software, update patches, and access websites, but someone from the internet doesn't need to connect to them. And so as a result of that, these do not need to be routable on the internet. And so a bright idea came from the Internet Assigned Numbers Authority, IANA, and they came up with the idea of having a range of IP address that they would use for private use only. So these are the three ranges that are designed or designated as private use. So you've got Class A, which is 10.network, 10.0.0.0, all the way up to 10.255.255.255. There are 16 million odd IP addresses in that range. There's a Class B network, 172.16.0.0, 172.31.255.255. It's a million odd IP addresses there. Class C network, which is our usual common, well-known 192 range, has got 65,000 odd IP addresses. This is important because there is the ability to use these ranges in multiple private networks. So your home network is probably using a 192 range. Your neighbor's network is also using that same range. And that's fine because they don't need to be on the public internet to be directly accessible from the public internet. There's also another range called the APIPA range, or the Automatic Private Addressing range. This is mostly for Microsoft networks. They had sort of come up with this range when Microsoft were busy getting into networking technology many years ago. So the key benefits of IPv4 address is this. You will see that these are three different companies, and they're all connected to the internet, but they all got the same IP ranges and even the same IP addresses. And that's fine. Maybe because they don't need to communicate, they don't need to directly connect to each other. They just need to get onto the internet. They might have branch offices of their own, in which case those branch offices need to be on separate IP ranges, but these companies are not going to directly talk to each other. They just need to connect to the internet. And so they can use those same ranges extensively. So the way how it works is the network allows you to send traffic to the internet using a gateway, or what we call a NAT gateway, which stands for Network Address Translation. Essentially, what's happening here is all of these devices are able to send traffic to the internet, and they will receive the response via this gateway. And the gateway, or the NAT gateway, has got an internal IP address to communicate with our internal devices, and an external public IP address so that it can be unique on the internet. This is why when you go into Google and you type in what is my IP address, it shows you your public address of your actual Wi-Fi router, of your actual modem. It doesn't show you your own private IP address of your machine. So it is that address that's being advertised on the public internet so that Google knows where to send that traffic back to. But you could have 3 devices or 3,000 devices. They could all be hidden in that private range space, and therefore you can have much, much more devices than just 4 billion odd IP addresses. Okay, so that was all about private IP addresses and NAT. So just to recap, so network address translation is a method of remapping one IP address space to another by modifying network address information in the IP header packets while they are transit over a routing device. And the NAT device will enable you to map multiple internal devices' private IP addresses to a single public IP address that the NAT device will advertise. This is what we call one-to-many NATing. NAT devices can offer security by ensuring that inbound initiated access from the internet is prevented and only allowed on certain ports. And also, those private IP addresses that I spoke about, those ranges, they're not actually routable on the internet. So if you took your laptop and somehow managed to connect to the internet, but you had just a private IP address, it just wouldn't work. So let's move on very quickly to talking about something slightly different. I mentioned the three different ranges, the three different private ranges. The way how these are displayed and provided and expressed is by using something called CIDRs, or classless interdomain routing. So let's talk about what that is. So you've probably seen something like this. You've got an IP range, and then you've got a /16. Okay, so this represents the network. This /16 represents the network size. And in fact, it also provides you information about how many IP addresses are in this network. And I'll come on to how that is in a second. So the /16 means that there are 16 bits of that 32 range we spoke about, that 32-bit range, that represent the network. The remaining 16 bits represent the number of IP addresses you can have in that network. So the remaining 16 bits is 2 to the power of 16, or 65,000 odd, 65,5336 addresses you can have in that network. That means if this corporate network is built with an overarching IP range of 10.100/16, then in this network, we could have 65,000 odd devices. One thing that you will find in networks, we don't normally do it with our home networks, but definitely with businesses and corporates, is that we create separate subnetworks, separate isolated virtual networks or virtual LANs, or as we like to call them in the world of the cloud, subnets, so that we can separate out different types of workloads. So we could have a subnetwork for all of our servers. We could have a subnetwork for all of our databases. We could have the subnetwork for all of the office staff and all their laptops and all their gadgets. And we could have a subnetwork for the sandbox so that the dev guys can do all their experimentation work. And maybe one for guest Wi-Fi because we don't want them accessing our material, right? So that when guests come, they go on a separate network altogether. That means we can take this large corporate network and break it down into smaller subnetworks. We do that for a number of reasons. One is to create isolation. Two, networks are very noisy, they're chatty. And so by doing it this way, unless someone in this office needs a direct access to a server, normal broadcast traffic isn't going to go through. Okay, so there's a lot of broadcast traffic taking place within your network. There's a lot of noise, and we want to avoid that getting into and clogging up our important stuff, right? Our important server room and our databases and stuff like that. So we isolate them. We create subnetworks. And unless you make a direct request tuned to that network, the routers don't send traffic across. There's also something called a public or a DMZ. DMZ stands for demilitarized zone. It's an area of your network that you want to expose out onto the internet. Okay, so for instance, your router has a DMZ area, an area that allows it to talk to the internet. In large corporate networks, we might have a designated DMZ network, a public network, where we will host certain services that we want to have direct connectivity from the internet. These might be web servers, they might be load balancers. In most cases, there will be things like your NAT gateway for network address translation, or they may just be some load balancers. And all of your other servers, even web servers, are all going to sit internal inside the network. What they do is they allow traffic from the internet to come through. There may be some firewalls, there may be some rules, there may be some port forwarding, so that only specific types of traffic are then allowed into the corporate network. So subnetworks are basically subsets of the larger network. So if this is a /16, which gives me 65 odd IP addresses, a subnetwork could be a /20. In this, what we're doing is, this is our main network, the one highlighted in the orange box. Then what we've done is we've gone ahead and borrowed an additional 4 bits from the actual host side of that network. And so what we have in total is we are now extending our 16 bits to an additional 4. So that's 20. So that's why it's called a /20. Also, what it means is because we've borrowed 4 bits, 2 to the power of 4 is 16. So if we borrowed 4 bits in this large network, we can have 16 subnetworks. In addition to that, what we have left are 12 bits of that 32-bit range. So in each subnetwork, we can have 4,000 odd IP addresses. 2 to the power of 12 is 4,096. So we can have 4,000 available IP addresses in each of these subnetworks. So I hope you're getting the picture here. We've got that large network. We've broken down into smaller subnetworks. Each network has its own designated purpose. And what we've done is, in order to make this all work, we've broken down our larger network into subnetworks using IP CIDR ranges. So we've got a /16 for the larger network. /20 is a smaller version or smaller subset of that. And we've broken it down and been able to allocate each of these subnetworks with their own specific ranges. Likewise, if you went for a /24, then what we're doing is borrowing 8 bits. So 16 plus 8 is 24. And so in each of these, we're going to have 256 networks, and each of those networks are going to have 256 IP addresses. So it's a much smaller network. Okay, before we go any further, what I want you to understand here is that the reason we've been going through all of this is because this is really important when you're building VPCs on the AWS platform. When you work with a client or in your business or in your corporate organization and you're going to build a VPC for them, planning and analyzing how you're going to build that VPC network and any necessary subnetworks is critical. So understanding IP address ranges in a lot more detail is really important. Now, I've got another video on my YouTube channel, which actually deep dives into how these numbers are arrived at. So if you are interested, do feel free to check it out. Now, in addition to IP addresses, we've got port numbers. So port numbers is a way of directing your request to a specific application on a server. Kind of like when you connect to a switchboard, okay? You're going on the main switchboard number, and then you want the marketing department or you want the HR department, that kind of thing. In a similar way, when you connect to a server on its IP address, you need to actually say where you want your request to go. Do you want to go to the mail server, the web server, the app server, the database server? And depending on which service you want, there are different port numbers for it. So let's talk a little bit about port numbers. So a port number is a way to identify a specific process or an application to which a network message is being forwarded when it arrives on a server. It uses TCP or UDP, and port numbers are 16-bit integers added to the header and appended to the message being transmitted so that the application, the server receiving it, knows when to send this request to. So examples include the HTTP port 80, RDP, which is Remote Desktop Protocol for Windows machines 3389, and so on. And again, if you're interested in knowing more about port numbers, check out that link, which gives you a full deep dive analysis into how port numbers work. So just a quick summary. So we've got a server over here with company A, and we've got Alice, and Alice is using her machine, and she wants to send an email to Bob in the other company. So she makes an email request. She uses an email client, Outlook, whatever it might be. And that is going to use the email service, so the email application on her server, to then forward that request. Because it's an email solution, by default, the port number for SMTP traffic, for email traffic, is port 25. So it uses these default ports because these are well known, and almost every company across the globe is going to use the standard ports so that we're all on the same page. And ultimately then, the service is going to send out that request to the recipient server, that email message,
And when it arrives at the destination, it's going to have that port 25 at the end and the packet header. When it reaches the server knows what to do with it. It says, this is an email message. It's SMTP traffic. I'm going to send it to the email service on my server. And then obviously that shows up in the customer's or the recipient's Outlook once it goes through all of the email application processes that it needs to complete. So that's how port numbers work. And again, port numbers are really important when we're working with VPCs on the AWS platform because they allow you to define what type of traffic you're going to allow into your VPC. So whilst we haven't spoken about VPCs just yet, bear with me, we're getting there. So there are some well-known port numbers that you need to be aware of. So port numbers from 0 to 1023 are called well-known ports. They're used by standard services like HTTP, port 80, or SMTP, port 25, and so on. Port 1024 and 49151 are registered ports. These can be used for services with the INA and should be treated as semi-reserved. Do you remember that RDP, Remote Desktop Protocol for Windows? That's 3389. So that's a registered port from Microsoft. Port numbers 49152 all the way up to 65525 are used by client programs. You're free to use them in your client applications. Web browsers connect to web servers. When a web browser on your machine connects to a web server, the browser will allocate itself a random port from this range. We'll come on to why it does that in a little bit. These are known as ephemeral ports. Okay, before we jump on into VPCs, are there any quick questions? Feel free to either drop that in the chat, or if you want to unmute, by all means, you can. Okay, in that case, we'll continue. I'll introduce you to VPCs on AWS. So here's the thing. We've spoken about on-premise networks. I briefly covered IP addresses. We spoke about how IP addresses work, what are CIDR ranges, and also, we looked at very briefly about port numbers. These are all important components and prerequisites in how you design a VPC and how you build a VPC. So let's talk about VPCs next. So VPCs, Virtual Private Clouds, is a virtual network that closely resembles the traditional network that you'd operate in your own data center. When you create a VPC, you need to define a region in which you want to create it. Now, AWS has multiple regions, a lot of regions in the US. In India, we've got regions in Mumbai and in Hyderabad. In the UK, it's in London. In Germany, it's in Frankfurt. In Ireland, it's in Dublin, and so on and so forth. These regions are a collection of data centers spread across what we call availability zones. Availability zones are metropolitan areas that are at least 60 miles apart from each other, where you might have one or more data center buildings. That comprises and makes what's a region. And when you create a VPC, it spans that entire region. So when you create a VPC, you need to say where you want to create this VPC. So if you're creating a VPC in the US, we could choose Oregon, for instance. It will span the entire Oregon region. If you want to create a VPC in the UK, it will span the London region, which will be multiple data centers across 3 availability zones. VPCs are isolated networks. Until and unless you allow internet-bound traffic outbound or inbound, it's purely isolated. You can't connect into it. When you create an AWS account, you get a default VPC in every region, which incidentally has an internet gateway to allow it to have internet access. So when you put stuff in the VPC, like servers or databases, they can actually send traffic to the internet. You can create your own custom VPCs, which is what I'll be doing in the live demo. There's a maximum 5 VPCs, but you can actually increase that, so that's not a problem. Services like EC2 instances, which are virtual servers like Linux, Windows, etc., need to be deployed in a VPC. Relational databases like Amazon RDS, MySQL, PostgreSQL, that kind of thing, also need to be deployed in a VPC. Redshift needs to be deployed in a VPC. A lot of services get deployed into a VPC. And so you need to create a VPC first before you can actually work with those services. Remember the 3 IP ranges that I spoke about? So that's the 10 range, the 172, the 192. Those are their default CIDR notations. So the 10 range actually has a default CIDR notation of a /8. The 172 has a default /12, and the 192 has a /16. On the AWS platform, the biggest network that you can have, the maximum network you can have, is a /16. So even if you choose a 10 dot range, you can only have a /16 network, which means that in that VPC, you can have 65,000 odd IP addresses. The minimum is a /28, which is 16 IP addresses. And obviously, as I mentioned, that default VPC has access to the internet because it comes pre-configured with an internet gateway. Also, let's take a look at the default VPC before we go any further. So the default VPC has a standard default CIDR range of 172.31.00/16. This is across all default VPCs across all regions. Also, the default VPCs has those subnets, those subnetworks I spoke about earlier. It's got one public subnet in each of the availability zones in that region. So if a region has 6 availability zones, then it would have 6 subnets across all 6. If it has only 3 availability zones, it'll have 3 public subnets across each availability zone. And one thing to be aware of is that the subnets, when you create them, the IP address must not overlap. This is important because when you're sending traffic from one subnet to another, if they overlap, the traffic is not going to get through. In any case, AWS will not let you create overlapping IP addresses for your subnets. So those are 4 different ranges. This is 172.31.00/20. You will notice that the larger network is a /16, and here we have a /20. So this network has got 4,000 odd IP addresses. The larger network, 65,000 odd IP addresses. But this range is different from this range. So this is 172.31.00 all the way up to 172.31.15.255. The next one starts at 172.31.16.0, and that goes up to 31.255, 32.0, 47.255, and so on. The default VPC is ideal for testing, generally not recommended for production use because you want to build your own custom network. And these only have public subnets, DMZ networks. You also need all of those private networks, right? Those server networks, those database networks. So by default, they're there for you to start working with VPCs, but you want to build your own custom VPC ideally. Some services expect the presence of this VPC, so by and large, AWS doesn't recommend that you delete them, although you could do if you don't need those services. And as I mentioned earlier, the default VPC comes pre-configured with something called an internet gateway. So any device you put in here, any server you deploy in here will automatically have access to the internet and will also have a public IP address from which traffic can come from the internet to that device. There's a default security group and a default network access controllers. I'll talk about those shortly. And subnets, as I mentioned earlier, are subnetworks of your VPC. One thing that you must bear in mind, especially if you're interested in taking the Solutions Architect course or any of the exams, is that the VPC spans the entire region, but the subnets span a single availability zone. One subnet, one AZ. And subnets are used to isolate workloads like we spoke about earlier, the server network, the database network, the office space, etc. Resources are deployed in subnets and are assigned public IP addresses. This is for the default VPC. So let's talk about custom VPCs next. And this is where we're going to start building a custom VPC so that you can get some hands-on, you can see how this is built out, and you can see how to build your own VPC in your account. So
When we create a VPC, we basically need to make some strategic logic and business decisions about what that VPC is going to hold. Generally, you build a VPC for a specific application. If you're taking one of my courses, then we have a lot of capstone projects. We've got 3 capstone projects that you will actually complete in the course that showcases or enables you to deploy application on the AWS platform called the Richer Roast Coffee Shop application. This is a complete end-to-end solution. So you get good hands-on practice of deploying from start to finish different components that help you build the application in the cloud. So I've taken this from that particular course just to kind of demonstrate how we build out a VPC. So the Richer Roast application comprises of basically a front end, a back end, and a database layer. And essentially, when you're making this decision as to how your VPC needs to be structured, you need to understand how you want to ensure high availability for your application, how you want to separate out the different workloads, how you want to separate out the front end from the back end, from the database, etc. And then accordingly, you will make decisions on how to build out that VPC. So we'll start off with a basic VPC shell. In this case, I've decided to choose the range 10.16.00/16. You don't need to use /16, but it gives me room to add multiple subnetworks and just have a lot of scope to expand. Now, as you know, the VPC will span all of the availability zones. So in the London region, we've got 3 availability zones. We've got 2A, 2B, and 2C. And we need to create an internet gateway. Okay, so the internet gateway will allow our resources to access the internet, download applications, download software, but also allow us to connect into the VPC so that we can access the application. So I'll be jumping on into the AWS Management Console in a minute, and I'll create a basic VPC shell. When you are building your VPC, when you work with different clients and whichever company you're working for, always leave room for expansion. The London region happens to have only 3 availability zones, but there's nothing to stop AWS tomorrow deciding on a 4th availability zone or a 5th or even a 6th one. So when you're building and documenting how your IP ranges should be defined, make sure you take that into account. So let's go ahead and create a VPC in my AWS Management Console. Okay, so here I am. I'm logged into my AWS Management Console, and I'm going to go into VPCs and quickly show you how to create a VPC. Now, as I mentioned earlier, when you create your AWS account, every region is going to have a default VPC. So you'll notice that there's one there already under VPCs. So if I click into VPCs, this is the default VPC. This is a public subnet only, public only VPC, and it's got 3 subnets. And it's got 3 subnets because it's got 3 availability zones in the London region. So each availability zone has 1 subnet. So we'll go ahead and create a VPC. So I'm going to click Create a VPC. And you've got options to either create a VPC from scratch where you build all of the components together and individual components, you define them. You can use a wizard to help you do that. I'm going to go with VPC only because I want to take you through the individual steps. So I'm going to call this one the Ritual Roast. You need to give your VPC a name. So I'm going to call this one the Ritual Roast VPC. And I think in my slide deck, I said it was, just quickly reference that, it was 10.16.00/16, right? 10.16.00/16. So 10.16.00/16. So that's my VPC CIDR range. That creates my VPC. Okay, it's just an empty shell VPC, nothing fancy happening there. If we take a look at this really cool feature called Resource Map, this allows you to see how the VPC actually looks. So currently it's just the empty VPC, no subnets. When you create a VPC, it creates something called a main route table. Now, route tables are really important. They allow you to define exactly how traffic is going to flow in the VPC, external networks out of the VPC, and so on. and even to other VPCs, because you can have VPCs communicating with each other over something called VPC peering or transit gateways. And then any kind of network connections within them. So currently all we have is just the empty shell VPC. Now, because we need to send traffic out to the internet, and obviously the plan is with this Richer Roast application, we actually build an app that's deployed in the VPC. So obviously we want traffic coming into the VPC, we need an internet gateway. So from the left-hand menu, you just basically need to create something called an internet gateway. There's one there already, that's for the default VPC. So I'll click Create Internet Gateway, and I'll give it a name, Ritual Roast IGW for Internet Gateway. Click Create Internet Gateway. So it's created the Internet Gateway, but you will notice that it's not attached to your VPC. So we need to attach it to the VPC. So we'll attach that Internet Gateway to my VPC, which is the Richer Roast VPC. One Internet Gateway, one VPC. That's the rule. So an internet gateway is a highly scalable gateway device that AWS will manage for you. You don't have to play around with it. Like your home network, you don't really have to log into your Wi-Fi router unless you're a bit of a techie. You leave that to Airtel or to Verizon or to the Sky or whoever it might be. In the same way, AWS manages the gateway for you, and it's highly scalable and redundant. So you don't need to worry about it. And so you just need to assign it to your VPC, which is what I'm doing over here. Okay, so if I go back to my VPCs and I click on this Richer Roast VPC, and I click on the resource map, you will see there is my Richer Roast gateway. There is no connectivity yet because I don't even have subnets yet. So we'll come on to that next. So far, I've got a VPC, Richer Roast VPC in the London region, so it spans the entire region, and one internet gateway assigned to it. Next, let's go ahead and see what we can do next. So next we'll add some subnets to the VPC. Now I mentioned earlier that the reason for creating subnets is because you want to create for isolation networks, subnetworks for different workloads, your servers, your databases, etc. In the case of the Richer Roast application, it's a 3-tier application. We've got a front end, a back end, and a database layer. For the purposes of the course, we actually combine the front end and the back end in the initial capstone project so that it's just the web tier, and then we've got the back end, which is the database tier. And the public subnet, the DMZ network, is used for things like load balancers. Let's take a look at how it looks visually. So here's our Richer Roast VPC. It's 10.16.00/16. Remember, the subnets are AZ specific. Subnets will define a subset range. We can use 10.16.00/20. And I hope you remember /20 means 4,000 odd IP addresses per subnet. And how many subnets you create is going to depend on a number of things, like how scalable or how expansive is your application? How many tiers does it have? And across how many availability zones you want to offer redundancy and high availability. You see, the purpose of the availability zone is for the high availability element. Let's say you deploy a web server in availability zone 2A, and that's just one single point of failure. If you deployed a copy of that in availability zone 2B, if 2A goes offline, because something goes horribly wrong, at least your customers can connect to the web server that's in 2B. So that's why we use availability zone for redundancy and high availability. Subnet IP blocks cannot overlap. Communication is possible across subnets with the VPC, within the VPC by default. And so that's how that works. So with regards to this application, what we'll be doing is we'll be using two availability zones. Availability zone EU West 2A and 2B. And within our VPC, we're going to be creating a public or a couple of public subnets. We're going to be creating a web app subnets. So this is where our servers running the web application is going to be hosted. And we're going to be creating a database subnets, one in each availability zone to offer that redundancy and high availability. Before we jump on into the console and actually set up these 6 subnets, I want to also talk to you about how it probably looks like in the real world, because this is just a lab environment. In the real world, you might actually have many more subnets. So in this case, we've got a maximum size of 16 and a minimum size of 28. That's the VPC default configuration. You can't have more than 16, so you can't have a /8, for instance. And each network, each VPC you create needs to have a minimum size of /28. That's the lowest you can go. You've got obviously public subnets and private subnets. Remember, public subnets are the demilitarized zone, where you put only those things, those resources that need to be accessible directly from the internet. So in the case of the London region, EU West 2A, 2B, and 2C, it's got 3 availability zones already. In the future, they may have yet another availability zone. So we want to make sure that we account for that. We want to plan ahead. And so here, I've got 16 subnets. Okay. And the reason why I have 16 subnets is because I want to ensure that as far as my IP address allocation goes, I have sufficient in case tomorrow AWS launches a 4th availability zone in the London region, I can expand into that zone. So I need to be careful how I design my IP address ranges. So we've got obviously the DMZ network across 4 availability zones, including one for future, the web, the app, and the data. And you'll notice what I've done here is I've split the web app layer, right? So rather than having just combined, rather than have the web and the app layer combined, I've actually decoupled it, okay? And the plan is that the application, when it goes into production, will have a decoupled architecture so that the web layer isn't tightly coupled with the app layer. And so when it comes to designing this architecture, the VPC itself is a /16, which is fine. That's the maximum size anyway. But because I need 16 subnetworks, because I want to think about the future and have another 4 in the future availability zone, so I need 2 to the power of 4. So that's 16 subnetworks. So if I'm using 16 subnetworks, then my CIDR range is going to be a /20. So each of these networks can be a /20. If I needed more networks, maybe because I had something else in addition to this 3-tier architecture, then I need to obviously change that. And so here I've done the same thing. I've borrowed those 4 bits to represent my subnetworks, and 2 to the power of 4 is 16. So I'm going to get my 16 networks, and I'm happy. And in each of those networks, remember there's only 12 bits remaining. 2 to the power of 12 is 4096. 4096 IP addresses in each of those subnetworks is way too much anyway, so it's going to be perfect. And so each of those subnetworks now have their own IP ranges. And they're not overlapping, which is really critical. Also, I'll leave you with one more thing before we jump on into the console, and that is on AWS, when you create a VPC, there are certain IP addresses that are reserved. Okay, so even when you create a subnet and you say, oh, I've got 4,000 odd IP addresses, 4,096 IP addresses, actually AWS will reserve some. So you don't get 4,096. It reserves 5 IP addresses. It uses this .0 for the network to represent the network. It uses .1 for the AWS router. It uses .2 for DNS. It uses .3 for future use. Again, we're thinking about future expansion. And .255 is always known as the broadcast address. You cannot use that address to assign it to a machine like a Linux server or a RDS database instance. So just be aware of that. Okay, so we've done the internet gateway. That's already in place. Let's go ahead and actually build out the subnets. So I'm back in my AWS VPC. And if I go onto subnets, I'm now going to create some subnets for my VPC. So you need to select the VPC you want to build the subnets in. So I'm making sure I select the Richeros VPC. I'm going to come down and start creating my subnets. So I'm going to call this one the RR public 01. So public 01 subnet. Okay, just quickly, I'll show you that diagram again. So it's this one that we're creating. So it's 10.16.0.0.20, 10.16.16.20. Okay. So the VPC is 10.16.0.0.16. And if you remember, this was 10.0.0.0.20. So we'll just do that. 10.16.0.0/20. That's the subnet range. Okay, the subset, and it's got that 4096 available IP addresses, but once it gets deployed, remember those 5 IP addresses are reserved for AWS. We'll add another one. So this one is going to be public O2. Also, very important, where is the subnet going? We need to define it. We need to tell AWS where we want the subnet. So we're going to put this in EUS2A. If you remember from the diagram, this is an EUS2A, and that one is an EUS2B. So we're putting it in EUS2A. Then when it comes to public O2, we're going to put that in EUS2B. That's 10.16.0.0.16 for the network, for the VPC. This is 10.16, and if we take a look at that diagram again, 16. So .16.0/20. Okay. Now let's create the web app subnets. So the next one is going to be the Richer Rose web app. Didn't want to put that in caps. There we are. Richer Rose web app 01. Okay. We'll do the same thing. We'll put this in EUS2A. That's the CIDR range for the VPC, and the CIDR range for the actual subnetwork was 10.16.64.0. So that's going to be 10.16.64.0/24. Okay, and then I'm going to quickly copy that, add another subnet. So this is our 4th subnet. This is for the web app layer. And that's going to go in 2B. And that's going to be 10.16.80.0/6/ sorry, that's 20. Yeah. Sorry, not 24, that's 20. So we're doing /20s. Just checking for all /20s, yes. Okay, so that's looking good. And then finally, we're going to do the database tier. So we add another subnet. So this is RR data 01, and the availability zone is EUS2A. And if I just quickly reference the diagram again, that's 192 and 208. So it's going to be 10.16.192.0/20. Okay, and then finally, the last subnet, the 6th subnet, /.2. This is going to go in EUS2B. This one is 208. Okay. So this is going to be 10.16.208.0/20. Okay, so just quickly, we go up again and we make sure we got everything right. So it's 10.16.0.0/16 for the network, for the VPC, the public subnet in 2A. So that's public subnet 1 in 2A, public subnet 2 in 2B, web subnet 01 in 2A, web subnet 2 in 2B, and then data subnet 01 in 2A, and data subnet 02 in 2B. And then we'll create subnets. And that's going to create the 6 subnets for you across the 2 availability zones. You got your DMZ, public subnet layer, your web app layer, and your database layer. And we've named them appropriately as well. So 2 data, 2 public, 2 web. So the idea is that our web tier combined with our app tier, which really you should split, is going to go in those two subnets. Our databases are going to sit right at the back in the data layer. And our public subnets is going to be used for any resource that needs to be exposed out to the public internet. Okay, let's get back to the slides. Now, we've created our subnets and we've got our internet gateway in place. The next thing we need to do is think about how traffic is getting routed in this environment. So if we were to deploy a server, a Linux server in the public subnet, normally you deploy stuff in the public subnet that needs direct access to the internet and for resources on the internet to access that service. So what happens is when you deploy a resource in the public subnet, you need to give it a public IP address. Okay, so you need to also then think about how you manage your route tables. Now, I mentioned right at the start that when you create a VPC, it comes with a default main route table. I'll show you where that is. So if we click on route tables, and I just do a refresh on this page, and you'll see here, if we just bring this closer, see this is the Richard Rose VPC. That's the main route table for the VPC. It says main over there. So I'm just going to call this one RR main RT for route table. Okay. And if we take a look at the route table, you'll see that it has a single route in it. A route basically defines how traffic is going to flow. So it's going to define the destination of that traffic. And you will notice that it is the same range as the VPC. And it's in an active state. This basically says traffic within the VPC can freely flow. That's all it says. So normally when you create subnets, they attach themselves to the main route table. Okay. Now, this route table currently only has an internal route, a route to allow traffic inside the network. There's no route to that internet gateway. There's nothing to say, you know what, send traffic to the internet gateway to get out to the internet. So we need to create a route in there. The problem is we don't want to do that on the main route table because every single subnet will by default attach themselves to the main route table. So here's what we do. We create another route table. We call it the public route table, and we attach the two public subnets, the DMZ subnets, to that public route table. And in that route table, we create a destination for the internet. So the 4 zeros/0 represents external network, which in this case means the internet, for example. And we define the target as the internet gateway. Now what happens is traffic from this device, if it's being sent to the internet, will automatically hit the IGW or the internet gateway, and it will send that across to the internet. We can also configure the public subnets to automatically assign public IP address to any device that is deployed in the public subnets, which makes sense. So let's do that. Let's jump into the AWS Management Console again, and I'm going to create a public route table. I'm going to associate the public subnets to that public route table. And the public route table is going to have a direct access to the internet gateway. So here we are on my AWS Management Console. We create a new route table. I'm going to call this one RR public RT for route table. Put it in the right VPC, which is the Richard Rose VPC. Then I'm going to click Create Route Table. So the route table has been created. Now, by default, it's only got that internal route again. We're going to add another route. We're going to click Edit Routes. I'm going to add a new one. And I'm going to add one for external networks or the public internet. The target is our internet gateway, which is there. And if we click into there, it will find, oh, we've already deployed an internet gateway. So that's good. So we'll select that and we'll save that route. Now the public route table has the necessary configuration so that any traffic for 0000/0 can be sent to the internet gateway. If we take a look at subnet associations, you will see that there are no explicit associations with this public route table. So we need to associate the public subnets, the DMZ subnets, to this route table. So we'll click Edit Subnet Association, and we'll select the public ones from the available subnets. And click Save Association. Okay. At this point in time, if I take you back to the VPC and take you to that resource map, you will see what's just happened. And in fact, let me just make it a bit smaller so you can see clearly what happened. So here's what's happening. So our Richard Rose VPC has got 6 subnets. The public subnets are connecting to the public route table, which is sending traffic to the internet via the internet gateway, as described in the blue squares. So hopefully you can see visually how this is beginning to look. Okay, so that part of it is done. Let's go back to the slides. Okay, so here we are in the slides. So let's talk about NAT gateways and why we need them. We've actually mentioned why we need them, but let's go into it further. So here we are back in our AWS environment. We've got that public route table connected to our public subnets, and we've got our main route table, which were already connected to the private subnets anyway. And we've defined that new route as well. Now, if we deployed a server in the public subnet and gave it a public IP address, it will be able to send traffic to the public internet because now that route is in place. So it knows where to send that traffic to. The internet gateway uses something called a one-to-one NATing. Remember, NAT gateway was one-to-many. Internet gateway does a one-to-one. So one public IP address, it will assign to one private IP address. If we've got 2 web servers deployed in the web app environment, by default, they will get a private IP address from this range, from the subnet range. You will see it's 10, 16, 64, and then 5 and 6. If this device needs access to the internet, currently, there's nothing here that says how to get to the internet. So we'll deploy a NAT gateway, kind of like your home router, which has a NAT service. And that NAT gateway is purposely being deployed in the public subnet because it makes sense, because it has to use the route to the internet, which is the internet gateway. The NAT gateway will also then be assigned with a public IP address. In the case of the NAT gateway, you need to assign it with something called an elastic IP address, which is nothing but a public IP address that never changes. It's static. Internally, it will also have an internal address. And then we will update the main route table so that any internet traffic is sent to the NAT gateway. In other words, we're piggybacking on the NAT gateway to send traffic to the internet from these devices. So then what will happen is, if this device makes a call to google.com, it will send the request to the NAT gateway because now we have a route to the internet. And the NAT gateway will forward it on through the internet gateway out to the internet to mrgoogle.com. NAT gateways offer one-to-many NATing, or another word of putting it is IP masquerading. So, NAT gateway features. NAT gateway must be deployed in the public subnet. They require an elastic, which is another word for static IP address, public IP address. It supports 5 gigabits of bandwidth and can automatically scale to 100 gigabits. This can be increased by splitting your resources across multiple subnets and creating a NAT gateway in each subnet. And NAT gateways are AZ specific, so the resilience is only within the AZ. So in the real world, you actually should be deploying multiple NAT gateways, one in each AZ, for high availability and resilience. The main route table must have the NAT gateway as the target, which I showed you a little bit earlier. And NAT gateways do not require, it's not required for IPv6. Okay, so just before we jump into the AWS Management Console, quick recap. We're going to deploy a NAT gateway. Okay, and in fact, let's do it this way. Okay, we're going to deploy a NAT gateway in public subnet 01, which is in availability zone 2A. And also what we're going to do is we're going to update that main route table. Okay, so let's do that next. So here on the left-hand side, if I scroll down, I'm going to click on NAT gateway, click create a NAT gateway, and give it a name. So this one is Richer Roast NAT-GW, something like that. And you need to say which subnet you're putting it in. I'm going to put it in the public subnet 01, as per the diagram. And I need to allocate it with an elastic IP address. I'm going to click this button to allocate it with a public elastic IP address, which is a static public IP address. And I got that IP address. And then I'm going to click create a NAT gateway.
Now, the NAT gateway takes a few seconds to become active and available, and it's currently in the pending state. Whilst it's doing that, we can update the route table. So I'm going to go to the route table, go to the main route table, click on routes. There's only one route. Click edit routes, click add a route to the internet, but this time pointed to the NAT gateway. Save changes. So we've done as per the diagram. We've got a NAT gateway in public subnet in EUS2A. It got a public IP address. We've updated the main route table. So now all services within these 4 subnets know that they can connect to the NAT gateway for internet traffic. Let's take a look at the web page again. And I'm going to go into NAT gateways. Still pending. It takes a couple more, a little bit longer, probably a minute or two. We leave that running as it is. Okay, so next, let's talk about network access control lists and security groups. So network access control list is a firewall solution. So in a client-server architecture, the client will pick a random ephemeral port. Let's talk about how this actually works. So you've got, say, Becky, who's got a client machine, okay? So her client machine is 192.168.7.2. When it sends traffic out to the internet, it will advertise the source IP and source port. Remember, I mentioned that it picks a random port number in the ephemeral range, and then a destination IP and a destination port. And the destination port is usually those common ports like port 80, 443, 25, whatever it might be, so that the recipient server knows what to do with that message. Here's Becky. She's using her client machine. Here's the Richer Rose web application. It's running on a particular IP range, and the service is being advertised on port 443, which is HTTPS. Now, when Becky sends the traffic, the client, her machine, will select a random port number from that ephemeral range. The port number is usually OS dependent. So if you're using Linux, it'll use a slightly different range versus Windows. Becky's computer establishes a connection with the server using that port 443, which is HTTPS traffic. And then the server can respond using its well-known HTTPS port. And now that it knows the client's port and IP, it can send the response back to it. So what actually happens is the initial request goes with this random port number, in this case 16789. The server receives the message, and it knows that it can send the response back to the destination IP, 192.168.7.2, 16789 port number. And that connection gets completed. Similarly, if she makes another connection later on, it will choose another random port number again. And that's how it works. The reason for this is to allow you to define all of your outbound and inbound rules as well. So when it comes to network access control lists, you have to define a client outbound rule and a server inbound. And they need to correlate. Now, obviously, Becky can access the Richer Rose website, and at the same time, she can access Google, Amazon, and Facebook. So each of those connections will have separate port numbers. And so that's how those different connections don't get all mixed up and jumbled up, because now we're using so many different port numbers in that wide range. So let's talk about network access control lists. They're basically a firewall that's applied at the subnet level. So any service we put in that subnet is now protected by this thing called the NACL firewall. When you create a firewall called the Network Access Control List firewall, you need to define an inbound rule and an outbound rule that corresponds to that inbound rule. So if I'm sending inbound traffic on port 80, I need to have a corresponding outbound rule that allows that traffic to go back so that the response can be sent back. So here we're doing allow inbound port 443 from the internet so that Becky, who's sitting at home, can send traffic to Richer Roast. And then we need the outbound rule to allow the entire ephemeral range, because we don't know what port number she's going to select at random, to the internet. So that's something to be aware of. So in the network access control list rules, we're going to allow inbound traffic on port 443 from the internet,
rule number 100, and you can have different rule numbers for your network access control lists. And then the outbound on the network access control list, we're allowing traffic on port 443 or traffic on TCP, but across the entire port range for the ephemeral port. Because like I said, we will not be able to predict what random port number Becky's computer chooses. So we need to allow that entire range outbound. Now, rules are numbered in order. The lowest number rule has the highest priority. This is important. Also, network access controllers allow you to define allow rules. So you can see allow rules here and deny rules. And that is really critical because I want to show you this diagram. This diagram says that rule number 100, we're allowing inbound traffic on port 443 from the internet. So everyone on this entire planet can connect to the Richer Rose web server and a Richer Rose customer application from the internet as long as they're connecting over port 443. But we've got a deny rule and rule number 50, where we're denying a particular range, a particular public IP range. Maybe because we think that there are malicious attackers or something like that, or we just don't want traffic from that range. You will notice that that is coming before the rule number 100. So rule 50 obviously comes before rule 100, and so that takes precedence. So what that means is if you need to deny something and then allow a more broader range, you should ensure that you build your rule structure in a manner so that you don't make mistakes. So in this case, definitely this range is going to be blocked because the larger range, the entire planet, is allowed, and that comes later on in the rule ordering system. So the lowest number rule has the highest priority. Also, when it comes to connecting to your different subnets, so we've got our web app subnet and our data subnet, you should understand that in order for traffic from one subnet to go to the other subnet, if we are building network access control lists, then we need to allow those specific rules inbound and outbound. And again, it's the same thing. So we're allowing it on a well-known port, in this case, the MySQL port, because this is a MySQL database on port 3306. But when we send the outbound traffic, we need to allow the ephemeral ports because we don't know what random port number that might choose. And so NACLs require these rule pairs, app database port and ephemeral port for requesting client. Now, AWS creates a default NACL for you for every VPC that you create. And in that default NACL, it's interesting. All traffic is allowed inbound and outbound. And you might wonder, well, isn't that a big security risk? And the answer is no, because in addition to network access control lists, we also have security groups. Now, if you build your own custom NACLs, then in fact, everything is blocked and you'll need to build it up from scratch. And in the real world, you might find that a lot of security-centric companies will not use the default NACLs. They'll want you to create custom NACLs. And then you need to define inbound and outbound rules very carefully. Because until you do that, everything is blocked. So next, let's talk about security groups. So security groups are firewalls that protect the actual resource. So if you deploy a Linux server, it's a firewall attached to the actual Linux server. More specifically, it's protecting the network card of the Linux server. So here's Becky again. We've already got the default NACL, which you remember allows everything inbound and outbound. And we've got the Richer Rose web server. Now, the Richer Rose web server obviously has a network card attached to it. And a security group is going to protect that network card. Excuse me. And what it does is it ensures that any traffic to that server, to that card, is blocked until you start creating allow rules. So here we're creating two inbound rules that allow traffic on port 443 and 80 for HTTP and HTTPS from the internet. So Becky can now connect to that web server and she's able to access that web server. Also with security groups, you don't have to define the outbound corresponding rule because security groups are what we call stateful. So any rule that's allowed inbound, any responses to those requests are automatically sent outbound. Another thing to be aware of is that with security groups, you can only create allow rules. You cannot create deny rules like you do with network access control lists. And that's important because then it means that if you want to create any deny rules, you do have to configure network access control lists. Also, how you reference your security groups is critical. So I want to quickly show you this. We've got the web subnet, and we've got the database subnet. We've got the richer rose web server that needs to update the backend database. Now, the richer rose web server is accepting traffic from Becky and her computer on port 443. But for the web server to talk to the database, we will be attaching a security group to the database as well. Okay. Now, this database security group will need to allow inbound traffic on port 3306 from somewhere, in this case, the web server. Now, if we've just got one web server, well, we use the web server's IP address. But that's not the best way to do things, because obviously you're going to have more copies of your servers for redundancy, for high availability. And so the question is, what if we want to scale and have multiple web servers? We can't do that because here what we'll need to do then is we'll need to have multiple rules from each web server ID. And it's going to be a manual effort because we don't know what IP is being assigned to each server that gets provisioned. And when they get terminated and new servers get provisioned, it's going to be a headache. So what we could do is we could have the inbound rule on this database server accept traffic from the entire subnet. That's one option. So we could allow inbound rule on port 3306 from the web app subnet IP range 10.16.64.0/20, the entire subnet. That's not really good either. What if in this subnet we've got richer rose web service, but we have another application, to-do list web service or automobile web service? It's possible. We don't want those servers connecting to our richer rose database. And so what we can do instead is we can have the inbound rule configured so that we allow traffic only from those servers that are associated with this particular security group, the richer rose web service security group. Now, every time we terminate or add new service into that group, they will all be able to talk to our database. And that's what security group referencing is all about. And it makes your environment more secure. So here you will see that this security group has an inbound rule that allows traffic on MySQL port 3306, but only from servers associated with the web server security group. So hope that makes sense. Okay, self-referencing is another component to look at, where what happens is sometimes you need different servers to talk between themselves. And so in this case, let's say all of these servers need to talk to each other. Then you need to have a self-referencing security group as well. Okay, let's go ahead and configure some security groups. So in this application, we'll be deploying some web servers and some databases. And obviously, we'll need traffic coming from the internet. We'll also be deploying a load balancer. This is what the application is when you actually take the course and deploy this capstone project. So in order for the capstone project to work, you will be creating 3 different security groups. You'll be creating a load balancer security group, which will accept traffic from the internet. You create a web app security group, which will accept traffic from the load balancer, which means that it will reference the load balancer security group. And you'll be creating a database security group, which will accept traffic only from those servers associated with the web app security group. This makes it highly secure, and it ensures that we are fully aware what resources are connecting to what other resources further in the actual VPC. So I'm going to quickly show you how to create those security groups. So from the left-hand menu under security, you've got the network access control lists. This is the default network access control list for richer rose. If you take a look, you'll see the inbound rules is allowing all traffic inbound, outbound, same thing. Now, if we take a look at the security groups, there's also a default security group, which you can just ignore. So we'll create one security group. So I'm going to call this one the richer rose load balancer SG. And the idea is this is going to accept traffic from the internet. okay? And it's the richer rose VPC. The inbound traffic is going to be port 80, which is HTTP from the internet. And we'll create that security group. So that's our richer rose load balancer security group created. And then I can create another one. This one is going to be the richer rose web app SG. We'll put a hyphen there. And the VPC is the richer rose VPC. And here again, I want to accept only the HTTP traffic, but this time I want to accept it only from the load balancer. So I will reference the load balancer security group. So other resources that are not related to my application should not be talking to my server. So now what we have is a situation where only the load balancer can send inbound traffic for the richer rose application to the richer rose web service. And then we'll create a third one. So this is the richer rose data security group. And richer rose VPC. And here, because it's a MySQL database that you will be deploying, sorry, not Microsoft SQL, MySQL. So there it is, 3306. That traffic is going to come from any of the web servers. And so if we scroll down, we're looking for the web server security group, which is that one over there. And so we'll scroll all the way down and click Create Security Group. And so at this point in time, we have our security groups configured correctly. Okay, what I want to do very quickly is go back to my VPC and show you that resource map again. I'll just make that smaller. And hopefully you can see what we've done so far. So we've got our richer rose VPC, we've got our subnets, we've got our route tables. So you'll see that the main route table is going to the NAT gateway. The public route table is going to the internet gateway. The public route table is only connected to the public subnets. The main route table is connected to the other 4 subnets. Now you can actually separate this out even more. So you can have the web route table, the data route table, and you can make it even more complex. That complexity just ensures additional security in how you design your architecture. So when it comes to actually deploying some servers, so if I quickly go into EC2, and I'm just going to quickly take you through a simple step. So I can go to EC2 to deploy a Linux server. I can click Launch an Instance using the EC2 dashboard. I can call this my web server, a Linux-based web server, a T3 micro instance, no need for key pairs. This is the area that I decide exactly where I'm placing it, the network settings. So I'll edit the network settings and I'll select my richer rose VPC. And maybe I want to deploy this server in the web app 01. And then obviously the web server doesn't need a public IP address, so it's disabled by default anyway. And I can select that existing security group we just created. So that would be the web app security group. And then as I scroll down further, I can have additional parameters like any IAM roles, or I can run a script when that server is installed to configure it with any applications, and so on and so forth. And then I can go ahead and simply launch my server. And my instance is now getting launched in the web app security group, specifically in EUS2A. So it's associating itself with the web app security group. So if we go into security, there it is. And it's currently getting deployed. So it's currently initializing and so on. And that's how you would then deploy your EC2 instances, your ECS clusters, your RDS databases, your Redshift data warehouse solutions, etc. in your VPC. If we go back quickly to the diagram, okay, something like that. Your architecture looks something like this at this point in time. And this is just quickly a snapshot of what we've built so far. So we've got our VPC, okay? We've got our route tables, we've got 6 subnets, and in the real world, you might have 16 subnets or 24 subnets. Again, it depends on the complexity of the application. We've only got the web and app tier combined together and the data tier, but in the real world, you'll have a separate web tier, a separate app tier, a separate data tier, and maybe even something else. A separate public DMZ area for maybe your NAT gateways, your load balancers. Obviously, you've got your internet gateway, and so on. So VPCs play a really crucial role in how you isolate different workloads, in ensuring security, and also ensuring that you only allow those specific types of traffic from those specific sources into your network. Okay. Right, let's just come out of this. So I'm open to any Q&A. If anyone has any questions, happy to answer those now. Feel free to just drop anything into the chat, or if you want to come and mute, you're welcome.
Yeah, Rajesh, Venkat here.
Hi.
Yeah, hi. Yeah, I have one doubt, like, can we deploy subnet on both availability domain, like shared kind of thing?
You can have a shared subnet. Basically, the subnet itself, so the subnet itself is actually within one availability zone, okay? But when you deploy a resource like an EC2 instance, it can have a network interface card in another subnet. So the subnet itself needs to be in one availability zone.
Okay, thank you.
Yeah.
Hi, Rajesh.
Or precisely in another subnet, but within the same availability zone. So you can have two subnets. So you have an EC2 instance, you deploy in subnet 1, and then it has another network card that's attached to another subnet, but in that same zone. Yeah, those are called multi-home machines.
Yeah. Hi, Rajesh. Kiran here.
Hi.
Yeah. So actually, I have a doubt. Earlier in the slides, you mentioned about VPC getting spanned across three availability zones, for example.
Yeah, so it
Yeah.
spans the region, yes.
Yeah. And in the previous slide to that, I have confusion where it mentioned that VPCs have got a soft something. There was one point where maximum 5 default VPCs, something like that.
Per region.
Yeah, maybe
Yeah,
one more.
maximum 5 VPCs per region.
Per region. Okay.
Yeah.
So
Yeah.
there's a difference, am I correct?
So what that means is that when you create a VPC, you select a particular region, say the London region or the Mumbai region or whatever. It will span all the availability zones in that region. But you, in your AWS account, can create up to 5 VPCs. So these are 5 separate networks isolated from each other across in that region.
So in that 5, okay. So 5, suppose I create one isolated network, so that will span across the availability zone, say for example in Mumbai region. So 3 availability zones.
Yes.
Okay.
Yes.
Okay.
But you can have 5 of those networks. So you can have a network for dev, one for prod, one for test, maybe something like that.
Yeah. Got it. Thank you.
Sure.
So Rajesh, if you want, we can increase the limit, right? Like.
Yes, it's a soft limit, so you can just raise a request and you will have that limit increased.
Okay.
Yeah.
Okay, thanks.
Okay.
And I have one more doubt, like we have the security group and the NACL, right? So both can be created for the subnet, like if we have both things, how it will work, like?
Yeah, so obviously what's going to happen there is the traffic is first going to hit the subnet. Whatever the subnet allows through, the security group can further filter that.
Okay.
So if the subnet is allowing port 3306 and 80 and 43, any resources in that subnet will be able to accept those, but they will be bound by what the security group then further restricts that inbound request.
In that case, if NACL is blocks and the security group allowing, in that case it will be blocked, right?
Correct. Yes, correct.
Okay.
Yeah.
Yeah. Which is why AWS, when they allow you to create your VPC, by default, their network access control list is all open, just to make things easy. But in the real world, you'll find a lot of companies will just not use that, and they'll create a custom VPC from scratch, custom NACL from scratch. And then obviously they'll build that first, and then the security group will further restrict any request, depending on which servers are in that subnet. By and large, though, you will find that only one type of resource is in a given subnet. You won't mix different resources or different applications in a subnet.
And this last one question. So
Yes.
is it only we should use these private IPs for creating the subnets or VPN?
Yes.
These
These are the
three
only
classes.
IPs you can use. Yes.
So if we use other public range, it won't allow, right, to create?
No, it won't allow. Yeah. So basically, the VPC itself needs to be in a private IP address space. What happens is when you create a resource with a public IP address, it needs to be connected. It needs to have a direct connection to the internet gateway for that public element component to work. So it's the internet gateway. It manages a table that basically says this public IP address translates to this resource's IP, private IP address on a one-to-one matching.
Okay. Yeah, thanks. Thanks, Rajesh.
Sure.
And also regarding, can you just briefly explain regarding stateful and stateless IPs?
Absolutely. So I had mentioned that security groups are stateful. So basically with security groups, you just need to allow an inbound traffic on a particular port, for instance, say port 80 from a particular source. The response to that is automatically allowed. So that makes it stateful. That means that security groups are stateful. Stateless is basically where you need to do both the inbound and the outbound connection. So if you're allowing inbound port 80 from the internet, you need to have a rule for the outbound request, for the outbound response to that request to go out as well. That's all it means. And that's stateless.
Yeah, got it. Thank you.
Sure. Okay. If there are no more questions, there's just a couple of things that I want to just quickly mention. I know we are almost 15 minutes left on our duration. So, I want to start off by basically saying thank you so much for taking the time to come and take this high-level training on VPCs. Obviously, if you are interested in the AWS Solutions Architect program, we're offering a project-based training solution. This is a self-paced training program. So it's currently in pre-release. And it is a project-based training solution. So essentially what that means is, in addition to all of the theory to help you prepare for the exam, our focus at the IIS Academy is to help you gain practical experience. So we've included with the training program 3 capstone projects where you will be building out the richer roast application, and you will deploy this application on AWS using various different technologies. You'll use the standard 3-tier architecture. You'll use containerization. So you'll basically upgrade and revise the application so that it's now being deployed using, say, for instance, ECS with containers and Docker and stuff like that. And then there's a final capstone project that looks at a serverless approach to that architecture. The idea behind the project-based training is, as I found, and a lot of my colleagues have found in the industry, is companies are looking for real practical skills. While certifications is really handy, showing that practical element is what's going to land everyone, that next job or whatever, and being able to demonstrate their skill sets to their potential employer. So you can use these projects to actually incorporate them, build them out, and then showcase them in your resume, on your LinkedIn profile, maybe even create, some YouTube videos or whatever it might be, and have a GitHub repo for demonstration so that you can showcase this as to how you build out these solutions. The purpose of the 3 capstone projects is to ensure that you are in a position to be able to, intelligently and actively talk about the different architectures as a solutions architect. So the whole course is designed to help you think as a solutions architect if you're interested in pursuing that track. Like I said, it comes with 3 capstone projects, and you can showcase your projects on your resume and LinkedIn, and you've got full access to the source code as well to showcase how it works. there's a special offer going for the next 24 hours. So you can get an extra 25% off if you use that code, if you're interested, on our website. And because it's currently in pre-release, it's basically where in the next coming weeks, the remaining modules, which only represent about 25% of the remaining course, will also be released. So by the time we get into September, we're already in August. By the time we get into September, the remaining course will be released. So it's currently at a 50% discount, plus there's a 25% discount if you're interested in signing up in the next 24 hours. In addition to that, obviously, some of you may just be embarking on your journey as we speak. Perhaps you're doing a career change. Perhaps you're working in a particular area of IT and you want to move into cloud. I'm also offering you the opportunity to have a 30-minute session with me for a career guidance session, and where I will basically look at your career track as it's been till date, look at your background and work with you to come up with a one-page roadmap, a career planner, so that you have different skill sets that you can plan for over the coming months to study for, to prepare for, and hopefully build on your career trajectory. So this is all available to you if you sign up with that special offer and take on the course, obviously. Okay, and the link to all of that is available in the description box, and obviously, feel free to check out our website, which is the iasacademy.com. And if there's anything else you need, or if you want to just have a chat about the training you had today, feel free to reach me out on LinkedIn as well. You can connect with me on LinkedIn, and I'll be happy to have any kind of discussions with you on this course, or perhaps if you're interested in taking the Solutions Architect course, or just a general chat. Let's connect. Thank you for your time today. Have a great day. Thanks, everyone.